Hello and welcome back to my channel. So in this video, we are going to learn how to solve a homogeneous linear differential equation, and we will also see a few examples at the end. Now, the algorithm to solve this homogeneous linear differential equation is as follows. So what is given to us? Given to us is a linear differential equation in which we have got the nth order derivative plus k1. K1 is a constant here because we are dealing with constant coefficient linear differential equation. So we have got k1 times the n minus 1th derivative of y plus k2 times the n minus 2 order of differentiation of y with respect to x. And finally, the last term is kn, which is again a constant, multiplied by y. And you know that y is the zeroth order derivative of y with respect to x, right? So this left hand side, this like the linear combination of all these derivatives is equal to 0. So this is the equation that is given to us. We have to find out what the expression of y is in terms of x, and that will give us the solution to this differential equation, which is linear and which has got constant coefficients. Okay, so what we need to do is, first of all, we will write the equation in the symbolic form. And as you remember from our previous video, that d power n is basically the capital D power n is basically small d power n by small d x power n. So this is the nth order differential operator, and dn minus 1 is the n minus 1th order differential operator. N minus 2 dn minus 2 d raised to the power n minus 2 is the n minus 2th order differential operator. And at the last, we do not have any operator here. It is actually d to the power 0, so we have just omitted it for the sake of brevity of writing the equation. So this is the symbolic form of the equation. In the previous video, we have seen an example of how to find out the symbolic form. You can always go back to that video and have a look at it. Okay, so we have got a symbolic form of the linear differential equation constant coefficients. Now what we do is that we write the auxiliary equation. The method to find out the auxiliary equation is to look at all the operators here, right? So in the symbolic form. So we take out the y from there and we equate this equation to 0, and finally we'll find out the roots of this auxiliary equation. Now, since the order of this auxiliary equation is n, the highest power here is n, we shall get n roots, right? And let us just name this roots as m1, m2, and so on up to mn. So we have got a linear differential equation with constant coefficients. We write them in a symbolic form, and then we write the auxiliary equation and find out the roots of the auxiliary equation m1, m2 up to mn. Now, let me tell you that the solution y depends on the nature of the roots of the auxiliary equation. So we are going to have again three cases over here. One of the case is that all the roots are real and different. Another case is that the roots are real, but there are some roots which are equal to each other. And finally, we'll go and understand and study the case where the roots are imaginary roots or they're complex numbers. Okay, so this is case one, when all roots are real and different. So the symbolic form of the differential equation becomes d minus m1, d minus m2, so on, d minus mn multiplied by y is equal to 0. So the first few terms over here, except the y term, is the factorization of our equation, right, of our auxiliary equation. Now, see, I mean, for this case, we'll look into the derivation of it, but for the next cases, we'll not look into the derivation because they're a little out of the scope of this video. Okay, so if we suppose look at d minus m1 and that of y is equal to 0, see, the d minus m1 is an operator again, right? So the operator of y is equal to 0. So that would give that like y as equal to c1 is a constant multiplied by e power mix. So the mi is the root of the auxiliary equation, and if we take all of those together, we shall get the equation, that the complete solution. As later we'll see that this is a complementary solution actually, but in the case of a homogeneous equation, this is the complete solution. The complete solution is c1 times e to power m1x plus c2 times e power m2x and so on, Cn times C1 times e power mn x. Please note here that m1, m2, mn, all of these are different from each other and they're real numbers. Right, so real numbers contain fractions, they contain rational numbers, they contain irrational numbers, positive, negative, zero, anything. Right, so the m1 to mn, they can be any real number, but the only condition on those real numbers is that they are different from each other. So this is the complete solution in case of in the case that the roots are real and different. The second case is that the roots are real and some roots are equal. So let's imagine that out of this m1 to mn, m1 and m2 are equal. Then the complete solution is given as follows. So for m1 and m2, apart from m1 and m2, by the way, everything else is same as the previous case. But when m1 is equal to m2, we shall write the coefficient of e power m1x. See, this could be m2x as well, right? So both of them are equal, correct? So this the coefficient becomes c1 plus c2x, right? So c1 plus c2x times e power m1x. And if suppose m1 is equal to m2 is equal to m3, so let's say there are three real roots which are equal, then the coefficient of e power m1x becomes c1 plus c2x plus c3x squared, where again c1, c2, c3 are constants. And from m4, if all of those roots are different, the expression remains the same as the case one, where all the roots were real and distinct. So this is the case 2. The case 3 is that there is a pair of complex roots, and the thing is that if there is a pair of complex roots, these roots must be conjugate. So what does it mean by conjugate? It means that the summation of these conjugate roots is a real number, as well as their product is going to be a real number. So these are called conjugate roots. Let's say that they are alpha plus I beta and alpha minus I beta. So this is a convention to use alpha and beta over here. You can very well use p plus iq and p minus iq, and basically when you solve this equation, you'll get numbers in place of alpha and beta. But anyways, the complete solution for this is given as follows. So e power alpha x, right? So the real part of x, real part of the complex roots is the coefficient of x in e power in alpha x, right? And that is multiplied by a number by combination, a linear combination of cosine of beta x and cosine of beta x. So e power alpha x multiplied by c1 cosine beta x plus c2 sine beta x, right? So this takes into consideration the two roots that are complex, and the other roots which are not complex, other roots which are equal, are like real but distinct, we place them later, as we had seen in the case 1. Okay, now let's look into a problem and let's try to solve this problem. In this problem, you see that we have got a differential equation and we have got two initial conditions here, right? So, like in order to solve any problem, we must find out what is the independent variable and the dependent variable. So here, t is the independent variable because you find t in the denominator of the differentiations of the differentials, right? And x is the dependent variable. Now we consider the operators over here. So dx is equal to dx by dt, d square x is also d square x by dt square. And once we have this, we will symbolic form of the given equation, right? So from the symbolic form, how do you get the symbolic form? Again, we substitute d square x by dt square in the given equation by d square x. We substitute dx by dt in the given equation by capital dx, and we keep x as it is, and we take the x outside, we get d square plus 5d plus 6, right? So now the next step is to obviously look at the auxiliary equation. So the auxiliary equation is d square plus 5d plus 6 is equal to 0, and that gives us d plus 2 multiplied d plus 3 is equal to 2. And from here we shall get m1 as equal to -2 and m2 as equal to -3. Okay, now so looking at this, our general solution is going to be c1 e power m1t, right? So m1 is -2 and c2 e power m2t. So m2 is -3 here, right? So that's how we get the general solution of our given equation. Oh, by the way, as you can see on the top of the screen, I have written that the auxiliary equation is also called the characteristic equation. So please do not get confused if you see the word characteristic equation somewhere. Okay, now the given condition x0 is equal to 0, what we do is that we substitute the value of t as equal to 0 here, and our xt will also be equal to 0. So we get c1 e power 0 plus c2 e power 0, right? That is equal to 0. And the second condition is d by dt of x0 is equal to 15. So we must find out what is d by dt of xt first, which is the given expression over here. Please note that e power at gives a multiply e power at as its derivative. So the coefficient of t comes down in both the cases, and then we substitute the t is equal to 0 and this expression as equal to 15, and that gives us another equation. So we solve these two equations and we get c1 as equal to 15 and c2 is equal to negative 15. Therefore the complete solution is 15 times e power minus 2 t minus 15 times e power minus 3t. So we get the general solution. We substitute the values by finding by plugging in the given condition, and we get the complete solution. All right, now the next problem is says that d square x by dt square is subtracted, from that we subtract 6 times dx by dt, and to that we add 9x, and that will give us 0. And there are two given conditions to us. So the method is exactly same. The only place where we should be careful is while finding out which case this problem belongs to. Okay, so first of all, the independent variable is t and the dependent variable is x, and we consider dx, like d and d square, and then we find out the symbolic equation by substituting dx for dx by dt and d square x for d square x by dt square, and we proceed by writing down the auxiliary equation. And as you can see, this auxiliary equation is basically d minus 3 whole square, right? So we get m1 and m2 as equal to 3. So this is the case where we have got a repeated root, right? So the root negative 3 is repeating. The root 3, sorry, it's not negative 3. m1 is 3, m2 is 3. So the general solution is xt is equal to c1 plus c2t e power 3t. So here, as you can see, ct is the independent variable. So we write c1 plus c2t, right? And this is the case 2 that we are dealing with. Now, as we remember, we need to find out the values of C1 and C2 using the given conditions. So the given condition x0 is equal to 2. Using that, we can substitute t as equal to 0 and x as equal to 2, which will give us C1, the value of C1 as equal to 2. And then we need to substitute the value of t as 0, and dx by dt is going to be 7, but we must find out what is dx by dt in the beginning, and our dx by dt is this expression over here, and we get this expression by actually using the product rule. So c1 plus c2t is kept as it is over here, and e power 3t is differentiated and written as 3 multiplied by e power 3t, correct? Okay, and e power 3t is kept as it is over here, and c1 differentiation gives 0, c2t differentiation gives c2, and that gives us, by substituting t is equal to 0 and the entire expression as equal to 7, as follows. So we get 3c1 plus c2 as equal to 7. And now we solve equation 1 and equation 2. So from equation 1, we already have c1 is equal to 2. So we substitute that in the next equation, and then we get c1 as equal to 2 and c2 as equal to 1, right? Okay, now since we have got the value of c1 and c2, we can write down the complete solution as 2 times t. So 2 is c1 and t is c2t multiplied by e power 3t, and that gives us, my friends, the solution to the given equation. And lastly, this is our final example in which we are going to solve d square x by dt square minus 4 times dx by dt plus 5x, which is equal to 0. And there is a set of given conditions where x0 is equal to 4 and dx by dt at 0 is equal to 5. Now again, t is the independent variable and x is the dependent variable, and we consider our differential operators as dx as equal to dx by dt and d square x by d square x by d square x by dt square. So this is, after doing this substitution, we get the symbolic form of the equation. So you see that symbolic form is d square x by dt square gives d square minus remains the same, 4 remains the same, dx by dt becomes dx, right, plus 5x, right? So 5x, there is no change in that, and we take the x outside because we are allowed to do so. Come on. And then we will write the auxiliary equation. Auxiliary equation is whatever is in this bracket is equal to 0, and that gives us, like two complex valued roots over here. So we get our roots of the auxiliary equation as 2 plus I and 2 minus I, right? So what do we do is that we solve the characteristic equation, right? Because characteristic equation, as we had mentioned earlier, and as you can see in the top of your screen, that an auxiliary equation is also called a characteristic equation. So this is the characteristic equation here, and from here we get the value of alpha as equal to 2 and beta is equal to 1, right? So alpha plus I beta is 2 plus 1, alpha minus I beta is 2 minus 1, right? So the general solution, this is a case 3 scenario. So e power alpha x, alpha is equal to 2 multiplied by c1 times cosine of beta x plus c2 times sine of beta x. So beta is equal to 1. So beta x, x was our independent variable when we wrote down our cases a few slides back, right? So here t is the independent variable and this is the general solution. So we substitute t is equal to 0 and xt will be equal to 4. That will give us our first equation as c1 is equal to 4. And then we'll differentiate this particular expression dx by dt, because we need to find out what is the, we need to substitute t as equal to 0 and x as equal to 5, and that gives us, like that differentiation gives us a pretty long thing, but it's very easy to understand and remember, because what we have done here is use the uv rule. So first we keep, to c1 cosine t plus c2 sine t as constant, and we find out the derivation of e power 2t, which is 2 multiply e power 2t, plus e power 2t is kept as it is, and we differentiate whatever is there inside the bracket. So this becomes negative c1 cosine t, right? And then plus c2 sine t becomes c2 cosine t. Okay, so now once we have got this, we substitute x as equal to 0 and dx by dt as at t is equal to 0 as equal to 5, and that will give us our second equation 2c1 plus c2 is equal to 5. So we substitute c1 is equal to 4 in our next equation, in the second equation, and we get that c1 is equal to 4 and c2 is equal to negative 3. Now, therefore, the complete solution of the equation will be e power alpha t multiplied by c1 times cosine of beta t plus c2 times sine of beta t. So, beta is 1, alpha is 3, and c1 is 4, c2 is negative 3. So, by the way, right? So basically, this is the equation, that this is the solution e power 2t multiplied by 4 cosine t minus 3 sine t of the given differential equation. Okay, thanks for watching. This was a pretty quick run through in each of the problems that we have discussed. Hope you enjoyed it. Thanks for watching. Bye.